All right, so today we'll be looking at limits, and in particular, we know there's a strong connection between limits and the behavior of functions. I don't have to tell you about the importance of functions. If you look around us, physical phenomena, they basically can be described by a function, processes in the universe. If you look at the gravitational collapse of stars from point of view of astrophysics, you'd find that the behavior of functions like the density of the star, its pressure, they all become very, very important as functions of, say, the radial coordinate, as well as the star collapses with respect to time. All right, so that's what you're going to be looking at. And how is the idea of the limit connected to the smoothness of a function, its continuity, differentiability, and the like. So that's basically what we're going to be looking at. But if you think of it, we've come across things like push yourself to the limit. What does it mean? All right, so let's just quickly have a look and see what we can make of this notion of a limit. Now, if I think of limits, I sort of tend to think of a sort of approaching a certain, let's say, the edge. Like for example, if you have a look here, you've got this river just in flood or flooding, and then you've got these objects as they get approach the edge, right? Not getting to the edge or over the edge. Let's focus on as they approach the edge, right? What basically happens at the edge, not over the edge, all right? Same again here, if you look at water pouring down a sinkhole, if you've got water coming through, you create this beautiful vortex. But as the water approaches that, I'm calling it a sinkhole. Well, if you look at the plug point, right, that's basically there. As it approaches, what actually happens? What causes that rotation? And the other one that for me, again, I could be biased from an astrophysics point of view is if you got matter being sucked into a black hole, for example, right, it's being driven, and as the matter gets closer and closer to the black hole, basically what actually happens, we know it will accelerate, right, towards the event horizon. And then the question is, once you've got this matter passing through the event horizon, right, now what's going to happen to the matter is going to move towards singularity. But as it accelerates, this process called accretion, then we're going to get sort of energy going out. I have something here that's quite visual as well. So I have in here liquid nitrogen. There we go. And what do you know about liquid nitrogen? It's a colorless liquid. It's very cold. The temperature is minus 196 degrees Celsius. And the science at this temperature gets very, very exciting. So I'll just pour some of that out into here so you can actually see. You're going to be very, very careful. You're going to have goggles, all right? Very important, closed shoes. And you've got to respect your experiments. So here, I'm just going to pour some out very gently into this container, or flask should we call it. And what's interesting about it is it starts to boil. So you have a look at it, you can hear that it's boiling away. What you're seeing out here is not liquid nitrogen, that's just water vapor, the air. And you notice the flask is getting very, very cold. But what, as I give this a bit of a twirl, you notice that how it starts to rotate. If this was water, you'd find that will slow down very quickly. But here, that rotation keeps going because if you have a look at it, the friction is minimized, but not to zero. But the question then I ask is the following, right? If we go beyond minus 196, and as we sort of in the limitless, so to speak, as the temperature approaches minus 273 degrees Celsius, which means 0 Kelvin, what actually happens to matter at that very low temperature, right? Look at that. Beautiful, isn't it? So as we approach 0 Kelvin, we can't get to 0 Kelvin, by the way, and the Heisenberg uncertainty principle sort of restricts us from getting there. But if you think of solids, liquid, and gases, the molecules in a solid, they sort of vibrate, right? But now as we cool that down, what's going to happen to the vibrations? They're going to slow down, they're going to slow down, they're going to slow down. And then what's going to happen as we approach 0 Kelvin? Could we produce new matter states, like what we call Bose-Einstein condensates? And what is this thing about dark energy and dark matter that people talk about in terms of the universe? So exciting things, but remember, we're speaking of limits here. As we approach, what does it mean? Not getting there into the singularity, not getting over the edge, but as we approach the edge, how does this function behave? And how do we handle the behavior of the various types of functions that we see out there. So that's basically what we're going to be looking at. And here's the liquid nitrogen. Still rotating quite nicely though, very, very cold. So, okay guys, we are back. Let's dive into the actual lesson now. And if I look at this parabola, it's defined by x squared, y equal to x squared minus x plus 2. And I'm going to ask a very simple question. All right, so there we go. There's your parabola, y equal to x squared minus x plus 2. And the question we want to know is, what actually happens as we approach x equal to 2? Now there's your x-axis here, right? And we're approaching 2, but you realize we can approach 2 from the left or the right of 2. Okay, so you look at situation down here, and as we approach x equal to 2, and this table basically, if you're having a look here, right, you notice that as we getting closer and closer to 2, right, closer and closer to 2, we expect to find that the y value, with the direct substitution in there, the function should approach a value of 4, right? We expect that. So we say that as x approaches 2, either from the left or the right, because if you look at the blue curve, it's smooth, it's continuous and well behaved, then the function approaches the value of 4. So in compact notation, what we can do is we can write the limit of this function f of x as x approaches 2, because of its smoothness and continuity, is 4. Okay, pretty straightforward. The limit of f of x as x approaches 2, not equal to 2, is equal to 4. It's simple as that. Right, so we look at a definition of the limit, and we say that as this function, as x approaches a finite value in some interval, and this is as x approaches a, then that function attains a value L, which we can see is the output on the y-axis over there, right? But it's interesting, and the question is, for example, what if the function is not defined at x equal to a? So we're getting close to the edge, but it's not defined. So we'll take a closer look at that and see what we come up with. All right. So here we have 3 different situations. In the first one, have a look at this first function. If I had to ask you to draw this one on the extreme left, surely you'll be able to draw this function without lifting your pen, right? Or pencil, or whatever you want to use to draw. And you'd find that this function is continuous, right? So it's defined. What I mean by that, for any interval on the x-axis from minus infinity to infinity, say, right, we could sort of sketch this function without lifting our pen up. So the function is continuous. It's defined for every x value. There is an output, a y value. So if we say as x approaches a, right, either from the left or the right, you see it approaches this value L. So as you get closer and closer, to a from the left or the right, you'd find that the output is L, right? So we say that the limit of this function as x approaches a is L. Now what's interesting over here, and this is quite nice, if you look at b, right? Now here you're going to pay careful attention. So just look at that there. So at x equal to a, you notice that there's a function, there's a little hole in there. So if you think of, say, electricity, it's almost like a switch being open or a broken circuit, right? Which means if you want to continue from the left of a to the right of a, right, you'd find there's a discontinuity in the function, right? So the function, so what we do is we plug the point in and we define the function at x equal to a, we give it a certain value, right, other than L. But you'll notice that as we approach a from the left, you'd find that the function is getting closer and closer to this value L, right? And if we approach a from the right, as we get closer and closer and closer to a, not at a, we find that the function is approaching L. So in this case, we say that the limit of the function f of x as x approaches a is equal to L. Similarly here, the limit of the function f of x as x approaches a is equal to L. All right, and here if you notice, again, as we approach from the left and as we approach from the right, the function is tending to the same limit L. So we say that the limit of the function f of x as x approaches a equals to L. And there we have it. So what we've noticed is the function may not be defined at a as you look at C. I think of C as a singularity. Think of it as that point in the black hole, you know, where the entire space gets sucked into a singular point, and there's like a T in space. There's a discontinuity there. And so we have it. So that's fine, not a problem. Just don't go there. Remember the waterfall? We're not going over the edge. We're approaching the edge. So we're approaching this singularity from the left, the right, but the function is getting closer and closer to L. I hope you see that. All right, so that's pretty cool. So let's look at this function over here. This is interesting. It says, and I put a sketch here to help you. So it says the limit of x minus 1 over x squared minus 1 as x approaches 1. Now, if you have a look at it, you think, okay, if I had to plot this graph. Now, the thing about limits, and I think we'd start this very quickly and very early on. If it says x approaching 1, do a direct substitution and you put x equal to 1 there, you get 1 minus 1. You're ending up with a 0 in the numerator. 1 squared minus 1. You're ending up with a situation where you've got a 0 over 0. And please, 0 over 0 is not 1. My soul will leave my body if you say that. So now we've got a case of 0 over 0. And so when you get this peculiarity, oh, did I say that? Peculiar. 0 over 0, infinity over infinity, that sort of stuff. We've got to think about that very carefully. But you would have spotted this and said, hey, hang on. This function, what does it look like? It looks like the limit of x minus 1 all over x minus 1 all into x plus 1 as x approaches 1. So there, that goes. Effectively, we've got 1 over x plus 1. All right. And so if you basically have a look at this function now, after its simplification, you've got a limit of 1 over x plus 1 as x approaches 1. A direct substitution will give you 1 over 2. So as x approaches 1 from the left or the right at 1, approaches but not x equal to 1, there's a punch, there's a break, the switch is open, the current doesn't flow, there's a discontinuity in this function. The function approaches a limit of a half, so that is 1 over 2. Does that make sense? It should, isn't it? Cool. So now let's think about this one. Again, we got x minus 1 over x squared minus 1. And if x is not equal to 1, so we look at all the points on the blue curve. But what we're going to do is we're going to plug that point. Remember, nothing's happening over here, right? But we're going to say, well, at x equal to 1, we're going to say that the function is equal to 2. So the question then is, what is the limit of this function as x approaches 1, not x equal to 1? And again, from the left and the right, you can see it approaches a common value of a half. So the limit of this function g of x as x approaches 1 is going to be 0.5. Okay, and you can see that it's defined as a piecewise function, which we did study earlier on. Okay, so what have we here? We got the limit as t approaches 0 of the root of t squared plus 9 minus 3 all over t squared. Now a direct substitution, you'd see immediately you're going to end up with something like a t squared, that's 0 squared plus 9, that's root of 9 minus 3, there's going to be a 0 at the top. And you've got at the bottom, you've got 0. So you end up with this peculiar case of 0 over 0. So then we need some little, I don't like to call it a trick, but some sort of inspiration to get through this. And the fact that you've got that root there, it sort of tells me let's multiply top and bottom by the additive conjugate. And so we're going to go root of t squared plus 9. There's a minus 3 over there, so we'd make that a plus 3. Top and bottom, by the way. So we are rationalizing, isn't it? Plus 3 like that. And what do we end up with? So the top you would remember from as early as grade, I don't know, 1, a minus b into a plus b becomes t squared plus 9. Don't forget that 3 squared becomes 9. And the bottom, what do we have? Don't forget, you're going to multiply that t squared. So you got t squared into root of t squared plus, you can see where the answer is going with this one. The 9 and minus 9 cancels out. How beautiful is that? The t squared and t squared, boom, goes away. And now you end up with, right neatly, the limit of 1 over the root of t squared plus 9 plus 3 as t approaches 0. Yeah, you're going to put 0. And the answer turns out to be, well, that's going to be 0 squared, root of that 3. And the answer is going to be a beautiful 1 over 6. And the world's a happy place. There we have it. Not too bad, right? Rationalization. Like I said, you get something funky like this 0 over 0. Be inspired. Let's see what are the little tricks or technique we can employ to further sort of progress with this problem over here. Very nice. Okay, so today, now, all this while we are talking about approaching a certain value from the left and from the right. So it sort of makes sense to think of limits being one-sided as we approach, say, a from the left and then approaching a from the right. Is it possible that a function could take on two different values, or right, as they approach a? So let's look at these things called one-sided limits and what can we learn from these. So it says here, and now this is very, very important. The notation can lead to, I'd like to say, widespread confusion. Now, if you look here, it says here, if the limit as x approaches a, and then you got this minus sign of f of x equals to L. Now, just let me clarify that a like that. And so when we say x approaching, that is equivalent to, right, x. So if you have a number line, that's probably the best way to do it. And there's your value a. You're approaching, not minus a, no, 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 no. You're approaching a from the left. So you're creeping up towards a, but from the left. Okay. And of course, if you got a plus, then you're creeping towards a from the right. So that's pretty straightforward. Nothing difficult over there. Whoa, what's this? Oh, yes, this is the AI, right? And PowerPoint, and you get all these beautiful little screens. So let's look at this function. It's a piecewise function. Looks beautiful, isn't it? I don't want to use green. No, it's too much of green. So if we have a look here, we say that the function f of x is the absolute value of x over x. And it's defined equal to 1 for x being positive, and it's minus 1 for x less than 0. But it's quite interesting, isn't it? Because if you think about that very carefully, for x greater than 0, what do we have? So for x greater than 0, if we go back to the definition of the absolute value, we know that absolute value of x is equal to plus x, greater than or equal to, by the way, and strictly, but less than 0. We know that absolute value of x is equal to minus x. Now this is interesting, because if I now write out this function in its two parts, it's piece by piece, then the limit of f of x as x approaches 0 from the right. So here we go. Why is it 1? Well, it's going to be plus x over x, which is 1. And then if you look at the limit of f of x as x approaches 0 from the left, that's going to be minus x, there's a minus sign, over x, which is equal to -1. So we have the one-sided limits as x approaches 0, but you notice they take on two different values, right? As x approaches 0 from the right, it's 1. From the left, it's -1. So we know that the limit, if you have a look, there's a disjoint, okay? There's a discontinuity, nice word. There's a jump in the function, in the step. And so the limit of this function of f of x as x approaches 0, right, that does not exist. While the one-sided limits exist and they're well behaved, but at x equal to 0, the function does not exist. Okay. Okay, guys, we're back, and now we'll look at, so pictorially, visually, this idea of the one-sided limit. So if you look at the first graph on the extreme left, right, you see as you approach a, if you think about that, let me just write this down. The limit of this function f of x, and we don't need to know the functional form because we got the graphic here, as x approaches a from the left, you notice that the function, although not defined at a, yes, it's defined at a in the sense that f of a is 2. You can see that here, it's plugged. But as you approach, you're actually approaching the value of 1. Now, if you're approaching from the right, the limit of f of x as x approaches a from the right, right, as you go here, you notice that the function itself is approaching a value of 3. And also you notice that f of a is defined to be 3. Okay? So this one, very similar, but we haven't plugged the hole. So we know that as we approach from the left, we know that this function, the limit is 1, and then from the right, the limit is 3. So that's straightforward. And similarly here, while the function is defined at a, as you approach from the left and the right, you see you've got those two holes there. But as you approach, you're getting closer and closer. From the left, you're getting closer. As you approach, you're getting closer to 1. And here, as you approach that way, you're getting closer and closer to 3. So that's straightforward. So here, f of a does not exist. Here as well, I mean, for the first part, as you approach, you can see that it is approaching the value of 1. It's plugged, so f of a is 1, all right? But if you think about it, in each of these cases, the function has this jump, and the limit from the left is not equal to the limit from the right. Hence, the limit at a, as x approaches a, does not exist. So that's something to take into account. Okay, so what about this function depicted in these three graphs? You got the extreme left, you got the middle, and the extreme right. So you'll notice that as x approaches a, right, from the left, from the right, so if I go the limit f of x as x approaches a from the left, that's what I mean, from the left, from the left, from the left, it's equal to the limit f of x as x approaches a from the right, right? Getting closer and closer. And what does a function do? What does a function do? It creeps up to 2, and hence if the left hand side limit equals the right hand side limit here, then the limit of this function at x as x approaches 2, not equal to 2, is going to be 2. All right, but it's interesting to see that in the left graph and the right graph, you notice there's a hole, there's a singularity that's there. There's a gap in the function. If you think of, as I said, fluid flow, current flow, there's a discontinuity in the function. While in the middle one, it's been plugged because we define f of a to be 3. All right, so just very important in this graph compared to the previous one. Here, the left-hand limits equals the right-hand limit, take on the same value as x approaches a. So the limit as x approaches, when I say a, I actually meant a, not 2, right? So we get the limiting value is 2. Cool. Oh, infinite limits. What does it mean? This idea of infinity being a large number, and it's interesting to think, and it brings to mind for me the book and the great mathematician, Indian mathematician, Srinivasa Ramanujan, The Man Who Knew Infinity. It's an interesting read. I think there's a movie on Netflix. You should actually go and have a look at it. But we're going to look at infinite limits involving, obviously, we're looking at running x from minus infinity to infinity, covering the real number system. How do we deal with this? And in fact, if you think about this very carefully, this, if you go back to school, would now be related to what we call asymptotes. Okay, so let's take a look at that and see what we mean by infinite limits. So here's some definitions. The limit as x approaches a from the left is positive infinity, from the right it's positive infinity. So we're trying to think of function just creeping up and jumping up like this. You would remind yourself from physics. I don't know if you remember this, especially I'm talking to people that don't learn physics by just doing past exam papers. Oh my goodness, that's not the way to do things. You remember this graph? Yeah, you remember that? Covalent bonding, you got two hydrogen atoms approaching each other, chemistry, and as they approach, you sort of feel their force of attraction, the force of repulsion between the two nuclei, repulsion, two electrons because it's hydrogen, repelling, and then the nucleus positive and the electron, and they would attract. But as you push them even further, closer and closer together, so that that potential, that electrostatic forces shoots up to infinity. So you have that sort of behavior. It's interesting that when we look at limits, we get a similar thing here, right? So let's take a closer look and see. Yeah, there we go. So we got a function 1 over x minus a, and you can clearly see here as x approaches a from the left and from the right, you have two different behaviors. So for the function here, this guy, the limit of the function f of x, as x approaches a minus, you see the function drops to minus infinity. Aibo. And then the limit of f of x as x approaches a plus, that means you're going here. See, it shoots up to positive infinity. So my question is, what's happening to that function? Let's recite, let's think about that. Stand in front of a mirror, share this with your friends. The behavior as x approaches from the left, as x approaches from the right over here, you see the function shoots up to positive infinity. And there you have this sort of singularity business, something weird's taking place over there. Don't go there. We're dividing by zero. And what does it mean physically when you divide by zero? It's interesting, isn't it? And then the question then I would leave with you is the limit of f of x as x approaches a. What is that? What is that? What is that? Think about that. And similarly here, you notice that from the left-hand side, you got x minus a. This tends to positive infinity with this 3 and a minus sign there. And then we have that. So we basically, by hitting the function with the minus sign, we are basically reflecting the graph about the x-axis. So think about the one on the right as well. Okay. So now, the previous one we went up to positive infinity. Here we're going down to negative infinity. So what happens to the limit as x approaches a of the graph on the right? What is the limit? Is it plus infinity? Is it minus infinity? Is it undefined? Is it infinity squared? Come, let's get some discussion going over here. Create a TikTok video. Share that with your friends on social media. Right, what is this? So the limit laws. The best way of learning these laws or rules is to apply them. Like you got the limit of the sum, then you got the limit of the difference, the limit of the product, the quotient, and then obviously the nth rule formula, right? For limits, what can we do with them? These are very useful, but I'm not going to learn them off. I am going to practice these laws by actually doing problems. I think that's probably the best way of learning them, rather than stand in front of a mirror and commit this to memory. That's going to be useless, right? Put in some useful information by actually doing problems. So let's see what's around the corner and see whether we can. The limits of polynomials. I like polynomials. They're smooth, they're well behaved, they do not give you problems. They sort of define for all values of x the real number system. So think of the quadratic ax squared plus bx plus c. All right, you had no issues with that when plotting the parabola, right, from minus infinity to plus infinity. Take the cubics that we sort of plotted and we differentiated. We found the turning points in grade 12. Smooth, nothing wrong with those. There were no problems with that. So with polynomials, if you look at the limit as x approaches a, we shouldn't have any issues regarding polynomials. And so if we take it's not almost a theorem, it's a theorem. So for any polynomial of this form of nth order, and if you want the limit as x approaches a, x approaches a, then we just say that it's actually equal to p of a. And the reason for that, it takes on every value of x in that interval from minus infinity to plus infinity. So you shouldn't have any problems with any polynomial functions because they are well behaved, smooth, and continuous. Think of all the graphs you drew in school. You could draw them. Right? I'm talking about the polynomial graphs, the cubics, the quadratics. You could draw them without lifting your pen up. So well behaved. All right, so let's just take a polynomial, any polynomial. So let's just call it p of x. And let's change the color there. So p of x is equal to minus x cubed plus 2x squared plus x minus pi. So the limit of p of x as say x approaches, let's choose a very difficult number, 2, is going to be, just plug that straight in, minus 2 cubed plus 2 into 2 squared. Oh, that's beautiful, isn't it? Minus pi, that's minus 8, that's plus 8 plus 2 minus pi. And so the answer is 2 minus pi. Beautiful continuous function, easy to draw, well behaved. Right. Okay, so what have we here? Interesting. Now the limit as x approaches 4 plus, I'm looking at part A, 2 minus x over x minus 4 into x plus 2. B, similar thing. C, similar thing, but there we're approaching from the right, from the left, 4 minus, and then as we approach 4, what actually happens? Well, first thing we recognize is we have an issue at x equal to 4, right? So if you look at all of these cases, we effectively, if we substitute x equal to 4 there, direct substitution I'm talking about, we have an issue. We're going to be dividing by 0. The numerator, if you put x equal to 4, notice it becomes minus 2. So the numerator, as x approaches 4, direct substitution, we can see that it goes to minus 2. Let's analyze the case where the limit of 2 minus x all over x minus 4 into x plus 2 as x approaches 4 plus. As we're getting closer and closer to 4, like say for example 4.1. So you'd find that the numerator is negative. 4.1, right? 4.1 minus 4, that's going to be a positive number. But as we hit 4, we're going to be dividing by 0. And then you got a positive number over there, 4.1 plus 2. So we're getting closer and closer to 4 from the right. And because the numerator is negative, then you can see that this is going to be minus infinity. All right? Because if the numerator was positive, then as we approach, look here, as we approach 4, there's the issue over here. That it blows up at x equal to 4, should we say. So as we approach, generally, if that was all positive, then the function will shoot up. But the numerator is negative. So basically what it does is it sort of flips it. And so the limit is going to be negative. So same on the other side. On the other side, if it's less than minus 4, take a value like 3.9. 3.9 minus 4 is negative. And then you've got negative on the top. So this one, the limit of 2 minus x over x minus 4 into x plus 2 as x approaches 4 from the left is going to be positive infinity. And of course, we'd say that does not exist because the limit from the left does not equal the limit from the right. So that is quite nice and beautiful. All right. So just watch, do a direct substitution, see what is actually happening in numerator denominator, look for the singularity where the function blows up, and sort of get an idea as you approach the region of blowing up, boom, 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 then basically what actually happens, but take into account the minus signs creeping up elsewhere as well. Okay, great. And then what is this one? X squared minus 6x plus 9 over x minus 3, a direct substitution in there. For the first one, what does that look like? That's going to give me 3 squared 9, 9, 18. That's going to give me a 0 over 0 case. So straight away we see 0 over 0 case. And then we look and we say, hey, hang on, but that is nothing more than x minus 3 all squared all over x minus 3 as x approaches 3. That tells me that there's a limit of x minus 3 as x approaches 3. Is that correct? And that's just going to give me 0. It's a linear function. But remember, if you're drawing that graph at x equal to 3, you're going to have a little hole there, a little discontinuity, or what we call an open switch. And so that would be an issue as well. So let's try this one. If we do a direct substitution here, we're going to get minus 8, you're going to get 0, and the bottom you're going to get 0 over 0. So then the question is, if that doesn't work, can we resort to factorization? So that's 2 into x plus 4, and I'm thinking there's going to be an x plus 4 here, and an x minus 3, isn't it? So that goes off as x approaches. Now it's minus 4, not 4 from the left. So what is that going to be? Direct substitution there would just be 2 into minus 4 minus 3, and that's minus 2 over 7. It's a finite number. And I'll let you think about this one. X squared minus 3x minus 10 over x squared minus 10x plus 25 as x approaches 5. Do a direct substitution, see what you get. I got a 5 squared 25 minus 25, so I got a 0 there. 25, 25, I got a 0 there. How do you deal with it? Check for factorization and see whether you can. So this actually turns out to be a 0 over 0 case as well. So see how you handle that. And I think we've got enough to have covered this type of question. Limits involving radicals. I haven't seen that word in a long time, but let's have a look at this. So we know what to do there. The limit, direct substitution, you got a 0 over 0, right? So 1 minus 1 numerator, so you got 0 over 0, right neatly. So what do we do? What do we do? The limit as x approaches 1, x minus 1 over the root of x minus 1, and then we know we don't want to change the problem, right? Change that. Multiply by the additive constant, rationalize, and so brackets, use brackets. Why not? Why not? So that becomes x minus 1 into root of x plus 1. And what's happening in the denominator? That gives you x minus 1. And beautifully, those will cancel as x approaches 1. And the answer turns out to be 2. And there we have it. So interestingly enough, just by rationalizing, we get a finite answer. We've got rid of that singularity or the problem, and there we are. Beautifully done. More to come. All right. Excellent. I hope you enjoyed this video. Okay, guys. So hopefully you're enjoying these videos. So don't forget to like and subscribe and even comment as well. So I'm going to be producing a suite of videos, differential calculus together with integral calculus. So please, enjoy the videos, make sure it's a really good excursion into calculus, and hopefully it's a great learning journey as well. So don't forget to subscribe, and I would also like to hear from you as well. Perfect. All right, so while you watch the videos, you see lots of images, examples coming up, and I really am indebted to many authors, many collaborators as we sort of start our adventure into the world of calculus. And so these two books in particular, Calculus by James Stewart, I think I used the 6th edition. Stewart Calculus needs no introduction. It takes me back 30 years or even more when I started working with the early edition of Stewart Calculus. What an amazing book. And really enjoyed calculus, the examples, the annotations, the graphics. And of course, it's it's improved, and it's going to, the latest edition is fantastic. Again, with also with Anton, Bivens, and Davis, the calculus there, beautiful illustrations, lovely examples, lovely explanations, a bit of history on calculus. And I think, guys, something we need to know as well when we look at, say, the Taylor series. Who was Taylor? Maclaurin series. Who was Maclaurin? Newton, right? The guy sitting under the apple tree, right? Really, really. I mean, what's his background like? What's his personal life like? Niels Bohr, Schrodinger, go through all of this. Sophus Lee, Felix Klein, some of the great names that come across, both in physics, theoretical physics, together with mathematics and applied mathematics. I mean, a lot of the calculus basically used in mechanics, fluid dynamics, thermodynamics. So, the applications are endless, and we're just getting started. So hopefully, this journey is going to be amazing. But like I said, I like to acknowledge some of the figures used together with examples, and I'm very privileged and honored to be looking at these books and also presenting it in my style. So thank you so much.